Okay, so previously we were talking about DFAs and we were being fairly loose. We didn't really have any sort of a mathematical definition of what a DFA was. And what we're going to do now in the next few slides is we're going to talk about how you can represent these mathematically so that we can write proofs about them. So remember that these are state transitions, right? And this really means if you're at state I and you next see the symbol A, then you transition to state J. But you can notice we could also describe this as a function, right? So this is T, our transition function, from state I on the symbol A results in ending up at state J. So here we've got a full state transition function represented as a table. So, here we say that if you're at state 0 and you see the symbol A, actually it should be lowercase a, right? Let's fix that. PowerPoint auto capitalized for me. But if you see if you are at state 0 and you see a lowercase a, then you end up at state 1, right? State 0, lowercase a, state 1. And if you're at state 0 and you see a lowercase b, you end up at state 2. There's your 0, lowercase b, state 2. So let's try something else. If you're at state 1 and you see a lowercase a, state 1, and you see a lowercase a, then you stay at state 1, right? If you are at state 1 and you see a lowercase b, state 1, lowercase b, you also stay at state 1. If you are at state 2 and you see a lowercase a, so you're at state 2, lowercase a, you stay at state 2. And if you're at state 2 and you see a lowercase b, you stay at state 2, which is what we said here. Good. So here you go, another problem. Let's just figure out the transition table for this DFA. So fairly straightforward, right? If I start at state 0 and I see an A, I will end up at state 1. If I'm at state 0 and I see a B, I am at state 3. If I'm at state 1 and I see a A, I end up at state 2. If I'm at state 1 and I see a B, I'm also at state 3. If I'm at state 2 and I see an A, I go to state 3. If I'm at state 2 and I see a B, I go to state 2, right? I stay at state 2. If I'm at state 3, state 3, no matter what, if I see an A or a B, I stay at state 3, right? So there's a 3 there and a 3 there. So there's our full transition table for this DFA. So here's a question for you. If we have the transition function, right, is that enough to reconstruct this whole DFA? And I'll tell you, I think the answer is no. Actually, I know the answer is no. Can you tell me why? So pause for a minute and think about it. And the answer is that I can think of 2 reasons why this is no good, right? First off, while we usually start at state 0, there's no rule that says we're starting at state 0, and a transition table doesn't tell us where we start. The other thing a transition table doesn't show us is which of the states are accept states. So in this case, state 1 is an accept state, and 0 and 2 are not, but here there's no way to represent that. So we need to have a little bit more information in order to reconstruct a DFA. So here's what our formal description of a DFA is going to include. It's going to include that transition table we've been talking about. It's also going to include a set that contains all the states that are in our DFA and another set that has our alphabet for our DFA. Now, of course, we could have figured out both of these things just by looking at the transition table, but we're going to specify it just so that it's really stated clearly. In addition, we're going to specify the start state, and I remind you here there's just one start state. And we're going to list, we're not going to list, we're going to put in a set all the final states. Of course, it's a set, so there could be 0 final states, 1 final state, 2 more, however many except states there are. Okay? So here's a formal description of a DFA. Here's a simple DFA that we've seen before. And we can just specify all the parts of it. So what are the states? Well, 0, 1, and 2. So we write down 0, 1, and 2. What's my alphabet? Well, it's the set AB because of these out transitions are for A and B. I'm just going to write transition function equals T, and then I will put T separately as a table because it's a pain to try and include all this in my list here. I'll tell you what the start state is. Right now it's 0. We can see that here. And what are the final states? What are the states that accept, right? And in this case there is exactly 1, and that's state 1 with a double circle. Formally, we're going to describe a DFA as a 5-tuple. So remember, this is a list. It's ordered. Order does matter. So we're going to first give you the states, then the alphabet, then the transition function, the start state, and the set of final states. So here is a description of this DFA. So my description says, first off, you need to know I have 3 states, and they are labeled 0, 1, and 2. My alphabet consists of 2 symbols, A and B. My transition function is specified by this table right here. The start state is state 0, and there is 1 final state, 1 accept state, which is state 1. And we can see here that's got the double ring. So here's a sample problem. Describe this DFA formally as a 5-tuple. And I've just reminded you here, because it's the first one, first the states, then the alphabet, then the transition function, the start, and the final. So let's see what we get. It's a 5-tuple, it's a tuple, so we're going to do a parentheses here. And we're going to start by listing the states. This has 1, 2, 3, 4 states, 0 through 3. So we'll write that down. My states is a set, 0, 1, 2, and 3. Next up in my 5-tuple is my alphabet, and it looks like my out transitions are on A and B. And alphabet again is a set, of course, so we'll say A, comma, B. Next, we're going to have the state transition function, right? And whenever I do this, I'm just going to put a big T, and we'll figure out that transition function in a minute. Next up, we need to say, what is the start state? No braces here because this is a singleton state, right? So I'm going to just say the start state is state 0. And what is the set of accept states? Well, there's only one accept state, right? There's my accept state with a double circle. So I will just say 2, and then I will close my 5-tuple. Not done yet. I still need to write the transition table for this 5-tuple. So here's a bit more space where we can write it. So make sure you say my transition table equals, and let's see. Our alphabet is A and B, and we have states 0, 1, 2, 3. Let me just shrink that down a bit so it's not taking over the whole page. So on state 0, if we have an A, we go to 1. If we have a B, we go to 3. So there's 1, and there's my 3. And if we're at state 1, on A, we go to 2, and on B, we go to 3. And if I'm at state 2 and I see an A, I end up at 3. If I'm at state 2 and I see a B, I go to 2. If I'm at 3 and I see an A or a B, I end up at 3. So there you go. There's my full formal description of this DFA. The first thing I tell you is the states, the alphabet. T is my transition function. There it is specified there. 0 is my start state, and my final states, my except states, are just one state, the state 2. So here's our last problem. We need to describe the regular expression that's given here. So it's either the symbol A just by itself, right? That's a string, just A, or ABB followed by 0 or 1 A's. That's what our DFA is going to accept. And we need to describe that as a 5-tuple representing a DFA. And I personally find that this is really hard to do unless you just draw the DFA and then turn it into a 5-tuple. So that's what I'm going to do. And the problem doesn't tell me the alphabet. I should probably ask the person writing the problem or the teacher what the alphabet is. For this one, let's just take the most obvious alphabet, which is the set containing the symbols A and B. Okay, so I'm going to squish that down so I have a bit more room. And let's see, so we need to have, there's my start, and we've got a state, oh, I was going to start with 0, but I guess I'm going to start with 1. And if we see an A, we end up at an except state, which we'll call 5, just to be creative, to show you you can name the states whatever you want. And we've now dealt with accepting the expression just a plain old A, but we also have to accept an A followed by 2 B's and then 0 or more A's. Well, this actually isn't too bad. If we have our first A and then we see a B, which maybe puts us at state 9, and another B, which puts us at state 27. You understand, of course, I'm just showing you weird numbers here to make sure you know that I can have whatever the heck I want. And actually, once we get to state 27, if you look, we could accept, right? Because it's A, B, B, followed by 0 or more A's. So state 27 gets a double circle. And we also need to accept any other A's that come in. And let's make that look a little bit more like an A. And let's kind of make another state down here, and we'll call this one, I don't know, let's call this state, let's see if I can draw a trash can. Does that look like a trash can? This is my trash state. And because nobody said we couldn't label a state with a picture, it's not exactly standard, but it's fine. So if we are at state 1 and we see a B, we go to the trash. Of course, once you're in the trash, you stay in the trash, so A or B stays in the trash. Harder to go through all the states here when they're not numbered, but we'll go through them sequentially. Trash is okay. State 1 is okay. State 5 has an out arrow for B, but no A. So I guess state 5 will send to the trash on A. State 9 has an out arrow for B, but not for A. And state 27 has an out arrow for A, but not for B. So there's my DFA. Let's shrink it down, put it up there for reference. So now we just need to specify that. Let's start with the transition table. That's the biggest pain, right? So here's my transition table. Let's do my horizontal lines first. How many states do we have? We have 1, 2, 3, 4, 5 states. So there they are. And our alphabet has two symbols. So our symbols are A and B. And our states are 1, 5, 9. That's 9. Let's make that a bit clearer. 27 and trash can. Right? So if you're at state 1 and you see an A, you end up at 5. You see a B, you end up at trash can. If you're at 5, A goes to trash can. This is why you don't really want to do these symbols. And B goes to 9. If you are at 9, A goes to trash can. And B goes to 27. If you're at 27 and you have an A, you stay at 27. If you have a B, you go to trash can again. And once you're in the trash can, you stay in the trash can. So there's our state table. But that's not our whole DFA, right? So in fact, I reminded you up here, here's our 5 tuple. We need to start with the states, then the alphabet, and so on. So let's make that just a little smaller. And we will say that's our transition table. And let's just move that up here so we have room for our 5 tuple. We'll put it right there. And so our 5 tuple for our DFA is a 5 tuple. The first thing we need to say is our states, right? So we have an interesting list of states. Today our states are 1, 5, 9, 27, and trash can. Set of states. We have an alphabet, which is just 2 symbols, A and B. Our transition function is T, right? Because we just called it T here. And our start state is just a single state, which is state 1. And the except states is a set, and it looks like it is 5 and 27. There's a close curly, and there's the close round bracket to close out our 5 tuple. So there you go.